Hi, I'm Sam Roberts from Roberts Geospatial Engineering. Today we're going to use virtual gridding in ProRaster Scientific to grid geophysical data. So we'll be looking at aeromagnetic data. So we'll be using the tensioned minimum curvature method and also the trend reinforced tension minimum curvature method. So let's look at our MRP file. Increase the resolution there. We're going to be looking at the micro level mag as the input channel. So there's our data. If I zoom in, you can see that we have north-south survey lines. Let's measure the distance between them. So a survey line is 400 meters. And we have these tie lines, which are 4,000 meters apart. And if we zoom right in, we'll see the individual stations, and you can see that the along line station spacing is about 7 meters, maybe 7.5 meters. So there's a significant asymmetry in the density of data across between survey lines and along survey lines, which makes this data, difficult to grid. It's traditionally been a problem in geophysics to grid this kind of data. When we grid it, we're going to want to eliminate the tie lines. So I'll demonstrate how to do that here in the rendering. I'm going to turn on the clipping component in the point lookup table color layer. I'm going to clip based on the band line, which has the line number. And then I'm going to use a data conditioning filter, this one, P1134 tie lines. Turn that on, and you can see that my east-west tie lines have disappeared. So this is just a simple method. We have these data conditioning filters, and in this one I've said that any line numbers between 190,000 and 199,000 and between 290,000 and 299,000, these line numbers represent tie lines, and so we can use that filter just to eliminate any stations in the data set that are tie lines, and we'll be using that in the gridding, the same kind of trick. So let's try and grid this data. Go to the point processing menu and select virtual grid. I'm going to select the MRP file as input. I'm going to put the put it there perhaps. That's my MVR, so this is my virtual raster, which is doing the virtual gridding. So let's go through some of these properties that you're likely to use. So firstly, in clipping. By default, we clip to the bounding polygonal union of the input MRP tiles. Now, for LiDAR data, we're going to have a lot of tiles, and that's a very effective technique. For these data sets, we probably have orders of magnitude less stations than you have in a LiDAR survey. So for example, this one we're looking at has 15 million stations. A LiDAR survey might have 15 billion stations. So I'm not going to use that clipping method in this case. Clipping to a polygon is probably a very good option, but we're not going to use that method in this case either. So firstly, I'm going to clip out my tie lines. So I'm going to clip by filtering. I'll choose that line band, choose my 1134 tie lines, and that's going to clip out all of the tie lines. And then I'm going to clip by distance. So my line spacing is 400 meters. If I put in a 200 meter clip distance, then in theory, if everything was perfect, every cell in the grid would be within 200 meters of an input data station or observation, and so it would not get clipped out. In practice, the lines vary around a little bit, so I'll put in a 250 meter minimum distance, and then as you scale that up, multiply it by 2, multiply it by 2, I'll make that 1,000 at the maximum level of zoom. So that's clipping by distance. We're going to use tensioned minimum curvature method, so I'm going to turn that on. I'm not going to change any of these options in tiles and padding. Then I'm going to choose my magnetic data, micro leveled, as my band data source. Now I want to set my cell size. Again, I have a 400 meter line spacing. I aim for 1/5 of the line spacing as a cell size when you're minimum curvature gridding. So that would be 80 meters. So I can just adjust this up to 80 meters. And then I want to make sure that at that cell size, I'm pulling all of the data from the data set. So I can bring this down until it says my point resolution level is 0 at the grid base resolution. Hit OK. And it's just gridded our data. Oops. Let's just maximize that. So this is multi-scale gridding, so it's gridded it at a larger scale, and then as we zoom in, it's going to regrid and bring in more data and grid it at a higher resolution. And so we're using we're using a lot of intensity scaling here, shadow. So we're seeing all of the information, we're seeing all of the detail, and we're also seeing all of the issues. So you can see with minimum curvature that one of the issues is this pearls on a string effect, this boudinage effect. So each line, remember, is north-south, so we get a data point along each line, and then between the lines it struggles to interpolate across those lines. So there are numerous ways that you can go about to try to improve that situation. So let's look at the minimum curvature gridding settings. So here's our gridding settings. So firstly, the number of iterations. There's no substitute for iterations in minimum curvature. The more iterations you can do, the smoother your grid will be, so it's good to do iterations. Unfortunately, that costs time, and that's why we have this convergence parameter. So in each iteration, we measure the difference between the value of a cell before the iteration and after, and we record the maximum change. And once that maximum change falls below this convergence value, then it stops iterating. So you can set this to a small value or even to 0, and then it will do more iterations. If you set it to 0, it will do the full number of iterations that you've asked for all the time. We have this relaxation parameter. This will generally be around 1.2 or 1.4, and that just might help it converge faster. We have our spline tension, so we're working with potential field data here, so I'm going to use a spline tension of 0, so there's no tension at all in the splines. We can apply a directional bias. So when we have north-south lines, it can be useful to apply some directional bias in the east-west direction, in other words, perpendicular to the flight lines. So we choose east-west and bump this up a bit, and that will help the system to interpolate across flight lines, which will tend to remove some of that boudinage effect. And then we have these other options for preparation of the data and for cells that are assigned values directly from data. So hit OK. There's our tension minimum curvature options. It'll regrid. Of course, the nice thing about the virtual gridding system is that you can go in and change your parameters and immediately see changes on screen. So now, for example, these east-west features are being quite nicely interpolated. We're not seeing so much of a boudinage effect along these features, but our north-south trending or more north-south trending features still don't look all that flash. So come back into our gridding options. Let's now turn on automated trend reinforcement. So I'll just switch it on for starters and we'll see what happens. Now, there are numerous ways that people have tried to automatically enhance trend information in gridded data. So there's a method that was developed by Richard Smith and colleagues at Laurentian University, and that's available in Oasis Montage. People have used techniques like anisotropic diffusion in image processing. This is a different technique. It's a technique that operates in conjunction with the minimum curvature algorithm. So as the minimum curvature algorithm is operating from low scale to high scale, or low resolution to high resolution, it's trying to detect trend directions, and it's trying to bias the interpolation in the direction of the trend at each pixel in the raster. Now, computationally, this is far more expensive than just doing minimum curvature. So you'll notice a significant degradation in performance, and as you can see, it hasn't yet updated. It's working on this grid now, and now it's beginning to upgrade. So for reference, the computer that I'm using today and recording this video on is an 8-core AMD CPU. And that's the kind of machine that you're going to want to do this sort of thing in real time. Anything less than that is going to be a little bit slow. But this particular machine, it costs $660, 8 cores, 64 gigabytes of RAM. So quite a nice little data processing machine and not expensive. So now that you can see that we've got good continuity along the flight lines and also improved continuity at an angle to the flight lines. And we'll be looking at examples. Rather than do this in real time, I'm going to show you some examples that I've prepared in advance, because doing it in real time does take a while. And we want to flip between minimum curvature and trend reinforced minimum curvature to see the difference that it makes. So let's come back to the properties. So go into our trend reinforcement properties. So there's a number of parameters here that you can fiddle with to change the effect. And this is a bit of a work in progress. It's likely that the default properties will change over time as I do more research and do more investigation into how this works and how it can be improved. But there are a number of things. So firstly, if there is a very dominant trend direction in your data set, you can bias the system to favor that trend direction. So you can turn this on and then say, I want trends at 67 degrees to be biased. The system looks at trends and it computes how confident it is that a trend actually exists in the data. And it gives a confidence value to those trends. You can then make the system reinforce trends over a range of confidences. So, for example, you can say, I only want to enhance trends that the system has a very high confidence exist. Or you can say, I want to enhance very low confidence trends as well as very high confidence trends. So there's a bunch of settings there. And then there are some other options. So when we detect the trend, you can look at the angular granularity. So there's some options here right down to a 5-degree angular granularity. We have an operator width, which you can increase and decrease. I don't think this makes very much difference. But what does make a difference is, firstly, our interpolation strength here and our filter sharpness here. So both of these things can be sharpened up to have a more significant effect on linear trends. So there's our trend reinforcement properties. As I said, it's work in progress, and over time we'll probably change the defaults, and we'll probably have default scenarios that you can select from. So for example, if you have you have a scenario like this where you have dikes running through a fairly non-magnetic background, there might be particular settings that are good in that scenario. On the other hand, if you have a setting more like out here when it catches up, where we have very high magnetic terrain with a variety of different trends, then there can be different settings that would be useful in that kind of terrain. So let's look at some example data.